like to invite and reintroduce our next keynote speaker, Dr. N. Sivaraman. Dr. N. Sivaraman is presently outstanding scientist and director. Okay, sir. We welcome you, sir. There's a small request. For any question answer round, we have a panel discussion in the end. I would request everyone to kindly make a note of their questions for the panel session.
Friends, good morning. I am Sivaraman. I work for Indira Gandhi Centre for Atomic Research, Kalpakkam, Department of Atomic Energy. Kalpakkam is it's about 60 kilometers from Madras. As we drive from Madras to Pondicherry, it is about 80 kilometers from Madras. 10 kilometers from Mamallapuram. I think architects might love to look at that place, Mamallapuram, built by Pallavas in about 700s to 800s. So Kalpakkam is located very close to Mamallapuram. It's a very special place, Kalpakkam, internationally as a nuclear complex, because we have three different types of reactors. We have a fast breeder test reactor at Kalpakkam. We have a Kalpakkam mini reactor, it's called Comini reactor. And we have two pressurized heavy water reactor. So what is special about that? The EBTR fuel is made of plutonium-239. Plutonium as an element is not available in nature. In nature we have element up to uranium with atomic number 92, mass number 235 and 238. So plutonium is man-made, and the EBTR reactor is basically fueled using uranium-plutonium mixed carbide, which is the unique fuel, and no part of the world has ever used this fuel. It's the first time in the world this fuel has been used. Not only that, this fuel has been utilized post-irradiation. It has been reprocessed. The unused uranium and plutonium has been put back into reactor. That means the fuel is seen complete fuel cycle. And no world has so far reprocessed the fast reactor fuel. And India is the first country to reprocess the fast reactor fuel. Of course, this is not a commercial reactor. It is a small reactor, but still it's a great achievement. We have a Comini reactor, Kalpakkam mini reactor, which employs uranium-233 as a fuel. Again, uranium-233 is not available in nature. It is man-made. What we do is we irradiate thorium-232, which is available in nature. India is the third largest thorium resource besides Australia and Brazil. So thorium captures a neutron, it forms uranium-233. And uranium-233 is a strategic material and it's wonderful fuel. It can be used in nuclear reactor fuel. The Kalpakkam mini reactor basically is a research reactor used for neutron irradiation, structural defects, post-irradiation examination, defects in materials, etc. And it's one of the wonderful facility, and the researchers all over the world, especially in India, come and use this facility. The third one is Madras Atomic Power Station. We have two reactors, pressurized heavy water reactor, which employs natural uranium oxide as the fuel, heavy water as the moderator and coolant. The first reactor was built in 1983, Madras Atomic Power Station, PHWR-1, and the second reactor in 1985. These reactors are operational for the past almost 40 years. In that way, this place is very special because we do use uranium-233, uranium-235, plutonium-239 in the same complex. So in that way, it's very special. I'll not just go into the details of that because we had already discussed. Look at the energy demands and the Per capita consumption is only about 610 kilowatt hours against the world average of 2,200, which was mentioned in the morning. So the indices of socio-economic development, longevity, GDP, etc. So we need to push forward these numbers. How does nuclear reactor work? I will cover in the later slides. The fuel is, instead of coal, it's a uranium oxide or plutonium oxide based fuels, and some of these other components could be similar. Let's have a look at it a little later. So worldwide energy, if you have a look at it, it's only about 6% coming from nuclear. So why I would say nuclear energy is inevitable option for India? Because of the meeting energy demands, ever decreasing fossil fuels, combating the climate change, long-term energy security. What are the issues from the public perception? Nuclear waste, nuclear safety, and public perception. Let's look at the nuclear waste. I shall discuss that during the course of my presentation. When a neutron interacts with uranium or plutonium, it induces nuclear fission. Nuclear fission involves splitting the heavy element into smaller objects. During the course of the fission, it produces enormous amount of energy. One atom of uranium or plutonium on fission gives 32 picojoules, one atom. So 1 kg of uranium-235 or plutonium-239 on fission will give you 1000 megawatt days of energy. 1000 megawatt days, if you calculate, 2.4 crores of units of electricity. 1 kg of uranium-235. That's enormous energy. When you do that, of course, you do get nuclear waste, we call as fission products and activation products. So what are the nuclear waste? Basically, of late, we don't call nuclear waste because quite a bit of useful material lies over there. We produce on nuclear fission of uranium about 25 elements which are naturally available, but they are radioactive in nature for various reasons because the number of protons to neutrons balance is not maintained. If you look at the atomic number of uranium, and sorry if I sound a bit technical, but during the course of my presentation I will make it general. Uranium atomic number 92, that means it has 92 protons or electrons. 235 or 238 is a mass number, that's about 140 neutrons. So there is a neutron balance, neutron to proton ratios are different. You look at the stable elements like iron, for example, the atomic number 26, gold 78, platinum 79, silver 47, etc. They have the balance neutron to protons. So when you build a heavy nucleus like uranium, the protonic repulsions are so high in a small volume of nucleus, the nucleus becomes unstable and it starts to emit radioactive rays like alpha ray, for example. So during the course of nuclear fission, you produce about 25 elements which are radioactive in nature because the protons to neutron ratios are not commensurate with what is required for stability. This includes cesium-137, which is radioactive, about 30 years half-life. That means after 30 years it becomes half of its initial amount. Strontium-90, a beta emitter. Noble metals, palladium, ruthenium, rhodium. Very interesting observation is the palladium availability in their crust is diminishing rapidly, and fast reactors are the biggest source of palladium because a fast reactor, 1 ton of fuel if you put in fast reactor, it produces 1 kg of palladium. And palladium is very useful materials in automobile industry, as a catalyst in chemical industry, etc. So the nuclear fission produces basically radioactive elements, cesium-137, strontium-90, two fission products which have got 30 years half-life. Besides that, we do produce capture products like americium-241, neptunium-237. So what do you do with the nuclear waste? Cesium-137 has a potential use which I would cover in the course of my presentation. Americium-241 and neptunium-237, these are the two radionuclides which are concerned because they got a long half-life. So the strategy is to recover them, put it in fast reactor and burn them. We call it as minor actinide burning. Once we do that, we would have addressed most of the concerns on nuclear waste. As we go on, I will discuss about the public perception as well. Look at the land size. I just quickly glance through that. The fuel required for running a 1000 megawatt electrical nuclear reactor is about 120 tons of uranium oxide. 120 tons of uranium oxide basically will give you about 1.2 tons of uranium-235, which is good enough. Look at the coal requirement. Almost 38 lakh tons are required to generate similar amount of energy. And look at the land size requirement, etc. One of the major advantages of nuclear energy, in my perspective, is almost negligible or zero carbon emission. That's the major carry forward. Just quick look at why certain elements are radioactive. Hydrogen, it has got 1 proton. Helium, 2 protons and 2 neutrons. Lithium, 3 protons, 4 neutrons or 3 neutrons, etc. When we go to uranium, in a small nucleus, the diameter is about 10 power minus 15 meters. So imagine how small the size is. You put 92 protons and some neutrons. If you put positively charged species, 92 in a small volume of size, the protons undergo repulsion. And this leads to instability in the nucleus, non-stability or instability. So it becomes radioactive. There are 3 ways it can undergo radioactive decay to stabilize to normal level. One, it emits alpha radiation, it emits beta, it emits gamma, it emits X-rays, and it emits neutrons. So these are the neutrons, these are the radiations that may be emanating from the radioactive materials, depending on the nature of material. So as I said earlier, if you split 1 kg of uranium-235 or 1 kg of plutonium-239, you would get about 1000 megawatt days. Where does the energy come from? A plus B gives C plus D. The mass defect basically leads to generation of that much energy. E equal to mc square, the mass defect into c square, if you multiply, you will get that energy. This is what happens in nuclear fission. A neutron, which is a subatomic particle, collides with uranium-235. It forms a compound nucleus, uranium-236. It splits the nucleus, produces fission products. One example is krypton and barium. There are a host of fission products which I was mentioning. And with large amount of energy. This is called nuclear fission. It forms a compound nucleus, splits into smaller fragments, plus 2 to 3 neutrons are produced. This is called chain reaction. When a neutron hits uranium-235 or plutonium-239, it produces fission products. It produces 2 to 3 neutrons. 1 neutron is used to sustain the chain reaction because that neutron will collide with another atom of uranium-235. There will be some neutrons which can be escaping from the fission, because some will be used for capture and the remaining neutrons will be used for breeding the fertile material like thorium-232. We can convert into uranium-233 or uranium-238 into plutonium-239. This is a fission chain reaction. A neutron hits uranium-235. It produces 2 to 3 neutrons. 1 is used for capture, 1 is escape, the rest is used for breeding. That is, 1 is sustaining the chain, the rest is for the breeding. Well, the nuclear fission was officially announced on December 1938 in the laboratory of Germany, Otto Hahn, Stossmann, and Lisa Meitner. I think I failed to put a photograph there. They established this is the lab of the Otto Hahn in 1938. Enrico Fermi was called the father of nuclear energy, Italian, who bombarded every element which is available to mankind in the periodic table with neutrons. He just missed nuclear fission because when he was doing the experiment, he was getting barium, an element. He was thinking that it's an impurity, and by oversight he missed the nuclear fission, and the honors were given to Hahn and Stossmann. But Enrico Fermi made a remarkable progress on establishing and maintaining and running the first nuclear reaction in a sustained manner at a squash court actually in the Chicago lab. So it's Chicago pilots called. All the legends are sitting down there and they're all in the team. EBR was the first reactor which was, which lighted the couple of bulbs there. It was established in 1951. Experimental breeder reactor. Indian Atomic Energy Program was established by the legendary scientist Homi Jahangir Baba. And Apsara is the first reactor in Asia which was operational. It is used for basically research reactor. Many neutron irradiation experiments are done at Apsara. Officially it was closed, now it is refurbished in 2018 with uranium silicide as a fuel. Naturally, uranium is available in the earth crust in the form of uranium oxide, we call pitch blende. Look at the isotopic abundance, uranium-238, which is not of great use, but you look at it, it's 99.3%, unfortunately. Uranium-235 is 0.7% because uranium-235 is more radioactive compared to uranium-238. Its population has come down. Uranium-238 has an half-life of 4.47 into 10 power 9 years, almost the age of Earth, 4.5 billion years, whereas uranium-235 has got an half-life of 7 10 power 8 years, so one order less. Thorium-232 is available in plenty in India, especially in the coast of Kerala. We have the third largest resource of thorium in the world. It is radioactive. It has an half-life of 10 power 10 years. That means after 10 power 10 years, the initial amount will become half. Of course, it emits certain radiation, the daughter products. These are the uranium resources in India, Rajasthan, Karnataka, Andhra Pradesh, Meghalaya, Jharkhand, Chhattisgarh. Our total estimate is about 100,000 tons of uranium oxide. Uranium has different oxides, U3O8, so UO2 is basically used as a fuel. So these are the typical uranium resources in India. So what is nuclear fuel cycle? The nuclear fuel cycle involves mining the uranium, converting the uranium into uranium oxide in the form of pellet. So small pellets actually. Once uranium pellet is made, it will be put into small tubes called clad. The clad basically ensures the protection of fuel, and it doesn't allow the fuel to come into contact with the coolant at high temperature. The clad material is basically an encapsulation. It will be made of stainless steel or zirconium based alloys. So once you make clad, you assemble the subassembly, put that into nuclear reactor. In pressurized heavy water reactor, we use uranium oxide as a fuel, heavy water as the moderator, and heavy water as the coolant. Heavy water is something like a light water with a different isotope. Hydrogen has 3 isotopes, hydrogen, deuterium and tritium. Heavy water is basically D2O. It is non-radioactive in nature, and India produces the largest heavy water in the world now. So we put uranium oxide as a fuel, heavy water as a moderator and coolant. Nuclear fission produces power, heavy water extracts the heat, and we operate the turbines and produce electricity. Once the fuel is used, the unused uranium plutonium will be recovered. We call it as nuclear fuel reprocessing. We do the waste management, isolate the nuclear waste. The unused uranium plutonium will be again put back into nuclear reactor, and the cycle goes on till you completely utilize all the uranium or plutonium. This is a typical nuclear fuel cycle. This is what I was mentioning to you. Uranium on interaction with the neutron produce host of fission products. A lot of energy comes out, and the plot gives what sort of fission products that are produced during the course of fission. That includes strontium, krypton, molybdenum, zirconium, noble metals like ruthenium, rhodium, palladium, little bit of tin, silver, they are produced in small amount. Then lanthanides, they are the major fission products. 1/4 of the fission products are lanthanides. We have two basically types of reactors in the world. One is the reactors which run on slow neutrons, we call thermal neutrons, and reactors which are operational on fast neutrons. Thermal neutrons means in the energy of 0.E5 eV. Fast neutrons is about 0.5 to 1 MeV onwards. The reactors, boiling water reactor, pressurized water reactor, they are all operational based on slow neutrons, whereas our FBTR, fast breeder test reactor, basically operates on fast neutrons. The difference is fast reactor basically use plutonium as a fuel. The function of fast reactor is not only to produce power, but to breed fissile material. In other words, we convert fertile uranium-238 into useful plutonium-239 or fertile thorium-232 into uranium-233. So this is what will happen in fast reactor. Not only they produce power, they breed fissile material. Whereas thermal reactors are basically used for production of only power. This is called breeding. A neutron, when it hits uranium-235, it undergoes fission. Whereas when a neutron hits 238, it forms a compound nucleus and it produces strategic material we call plutonium-239, which is useful fuel material. Thorium is converted to uranium-233, whereas uranium-238 is converted to plutonium-239 by a series of nuclear reactions. So when Atomic Energy Act was established, Homi Bhabha envisaged three-stage Indian program. The first stage is pressurized heavy water reactor. Initial collaborations with Canada, so Canadian deuterium uranium based reactor. Subsequently, all the pressurized heavy water reactors are indigenous. They were all established, totally made in India. The function of pressurized water reactors are to produce nuclear power, produce plutonium-239. The plutonium-239 will be fueled in the second stage, fast breeder reactor. Basically, plutonium-uranium based fuels, and the uranium-238 will be effectively or completely utilized in fast reactor. So fast reactors basically produce power, they breed fissile material. And the third stage, it was envisaged, was to drive uranium-233 based fuels along with thorium. This is we have now come up to the second stage. Third stage is operational in a small scale. These are the nuclear reactors available. Some are operational, some are to be commissioned. That includes Kalpakkam, Kudangulam, and Kakrapara, Tarapur, Kaiga, etc. And there are many other proportional contributions from other places which are planning to be established. So there are about 22 reactors currently operational, producing about 6,800 megawatt electric energy. Just quick glance at the Tarapur Atomic Power Station, Rajasthan, Madras Atomic Power Station. These are the other reactors operational, Kakrapara, Kaiga, etc. So the major, there are about 437 nuclear power reactors in the world. Basically, 67 reactors are under construction in India, China, Korea, Russia. So this will add to the additional energy. So I already spoken to you about fast reactors. They are the major source in the future because they not only produce power, they produce more fissile material. This is our fast breeder reactor at Kalpakkam. It produces power, but look at the bottom. We have a facility for production of a nuclear medicine called strontium-89. Because nuclear medicines are expensive and no country will provide India the nuclear medicine. Strontium-89 is produced at our Kalpakkam site by irradiating a neutron with yttrium. We produce strontium-89, we purify that. Currently it is under biodistribution studies. Shortly we will be in a position to supply strontium-89 through BRIT to the various hospitals. It's a bone palliative medicine because you know that the metastatic bone cancer patients at the terminal stages, they will be put on morphine patch and it's impossible to keep them. And there are two isotopes, one is samarium, other is strontium. Once you give a strontium-89 injection, the patient will be feeling comfortable for about 6 months. So 2 doses per year will be adequate. And this production is currently underway at our reactor center, strontium-89. Besides that, our center is also used for other neutron irradiation experiments, etc. So what's the way ahead? Because one of the questions whenever I meet students or the common public is nuclear reactions, radioactivity, waste, etc. The concern. What is alternate is the nuclear fusion. Nuclear fusion involves fusion, combining smaller elements. Hydrogen, 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 deuterium, deuterium, tritium. Why not heavy elements? Heavy elements are difficult to combine because the protonic repulsions are so strong, you cannot combine two heavy elements. Whereas two lighter elements could be combined by giving or providing an appropriate amount of energy. This is called nuclear fusion. Lighter elements are combined to form a relatively heavier element which releases a lot of energy. What's the limitation? To initiate the reaction, you need to provide large amount of energy. So India is part of about 10 countries which are involved in the ITER, France, for nuclear fusion. Another interesting development the last week from the Lawrence Livermore Laboratory, United States, they have come out with 2.5 megajoule energy to sustain the nuclear fusion. These are the early days, but my strong perspective is in another 40-50 years nuclear fusion could be in race for production of power, because there is not much radioactivity, no minor actinides, etc. So this will be in a very, very interesting technology way forward. This is a fusion energy. What they do is they shine high energy on deuterium, tritium, conduct fusion and release the large amount of energy. Attractions of nuclear fusion, unlimited fuel, because it's only, what happens in sun is basically, the sun energy comes from nuclear fusion. Hydrogen gives H2, H2 plus hydrogen gives 2 helium-3 plus hydrogen gives 2 helium-4, etc. This reaction basically runs the, the energy in the sun. So unlimited fuel, no CO2, no air pollution, major accidents difficult to foresee, no radioactive ash, and would meet an urgent need of the energy. Before I close my presentation, I thought I can share what we do in terms of radioisotopes, nuclear medicine we produce, and these nuclear medicines are supplied to all over India through different hospitals. It is done by our another unit, Board of Research for Isotope Production. So what, besides nuclear power, not that we produce only nuclear power, medical applications, industry, agriculture, age determination, etc. A few examples I'll quickly glance through. The medical imaging, starting from X-rays to PET, positron emission tomography. The first application you all know. You can guess who is the person. First person in physics to win Nobel Prize, 1901, Röntgen. So what he has done, X-rays, discoverer. The first shot, the X-ray was his wife's ring actually, 1901. The rest is history. The imaging technique started to dominate. This is William D. Heavisey. He introduced the tracer principle, 1943, the birth of nuclear medicine. What is nuclear medicine? Nuclear medicine is a radioisotope which is given either for diagnosis or therapy or both. We call it as radiopharmaceuticals. Some are used for imaging techniques. What are the isotopes? There are a host. Strontium-89 is produced at IGCA Kalpakkam. Bhabha Atomic Center, Bombay produce ruthenium-106, which is used for eye cancer, especially for the children. Cobalt-60, India demands enormous. We produce only about 60%. Cobalt-60 is used for cancer irradiation, basically, cancer therapy. It is also used for food irradiation, basically, because you know that the mangoes which are exported to United States and other countries, it is mandatory that they should be exposed to gamma rays to kill all the germs. These are the various other isotopes that are produced in nuclear reactors for various medical applications. The very interesting one is thallium-201, below, diagnosing coronary artery disease. Technetium-99 is man-made. It is produced by irradiation of molybdenum and cyclotron. It is used in image skeleton, heart, muscle, etc. If you go to any other major hospitals, it is inevitable. So technetium-99 is one of the most extensively used nuclear medicine across all hospitals. It's a workhorse, it has got a half-life of 6 hours. What we do is you inject technetium into patient in the form of a phosphorus complex. The body absorbs, and based on the gamma radiation that is emitted, the doctors would identify what are the issues with the patient. So just one quick photograph, normal patient. Technetium 99M, metastable, 6 hours half-life will be injected in the form of diphosphonate, a particular compound, so the body will try to solve that. The amounts given are very small in nature, they have got a less biological half-life, they will be excreted through body fluids, so there won't be any issues. The patient will be quarantined for about 8 days. So used for multiple metastasis. It's one of the most utilized radiopharmaceutical all over the world. Iodine 131 is another frequently used isotope to identify thyroid deficiencies. It's a very, very simple method. The patient will be asked to drink orange juice spiced with iodine 131. It's man-made in our reactors. It has got a half-life of about 8 days. And based on the iodine sorption capacity, doctors will quickly get to know what are the issues with thyroid. And it has got a very short biological half-life. About 3 to 5 days the person will be quarantined, and after that he will be discharged in hospital. So one of the most extensively used method. These are all produced. Positron emission tomography, you know, most of the hospitals now, they get to have this PET scan. What they do is, they produce in our atomic energy fluorodeoxyglucose, F18. It's labeled molecule. It mimics your glucose in the body. Once you suspect the person is having a cancer, they give FDG. And let us have a look what will happen. This is FDG. And the body absorbs fluoroglucose. The cancerous patients have that, the cells will have the tendency to absorb more glucose compared to normal human beings. So from the gamma emission pattern, because the FDG basically produces 2.511 MeV gamma rays, and from the imaging easily you can pick that up whether the person is having a cancer or how far it has spread. So, therapy, well, cobalt-60, as I said, it's one of the most extensive used for cancer therapy. Cesium-137 is another nuclide which I said is present in the waste. It is isolated. It is used for the blood irradiators. So these two are the big sources in the years ahead, cobalt-60 and cesium-137. Radiography has got enormous applications in industry. Because of the time I'm not getting into that. Isomed facility in our BARC and other places, they use this. They use about 1,000 kilocurie of cobalt-60. It is used for sterilization of all the medical products, food irradiation and many other applications in agriculture, etc. Age determination, Frank Libby is from the Princeton lab. He proposed that C14, which is there in the atmosphere, it has got a half-life of over 5,800 years. As long as the plant is living, the C14 to C12 ratio remains constant. But once the plant is not living anymore, the ratio changes, by which you can measure the age of the plant. Agriculture applications, how the plant absorbs, etc. Phosphorus 32 is another interesting radionuclide. This is what I wanted to, when I was talking to you about the public perception. Look at the person, Marie Curie. She is basically Polish. She worked with radioactivity. She won the Nobel Prize in 1903 along with her husband Pierre Curie and Henri Becquerel. They shared the Nobel Prize. She lost her husband in a road accident in 1905. She brought up her 2 daughters, Irene and Eva, produced another Nobel laureate through her daughter, Juliette Curie. What she says, nothing in life is to be feared, it's only to be understood. Now is the time to understand more. So that she handled tons of material and isolated radium and polonium. So only woman to win 2 Nobel Prize, one in physics, one in chemistry. 1903, along with her husband Pierre Curie and Henri Becquerel, and 1911 for radium and polonium. Look at her laboratory. I don't have time otherwise. It's a remarkable human being. The perseverance, working under trying conditions, losing her husband, bringing up the children, everything she has done. And Another legendary person who I admire always is Homi Bhabha. Unfortunately, he died early. Born in a very rich family, Homi Bhabha. It's a family business. Father requested him not to pursue, take on business. But somehow Homi Bhabha felt his mind was in physics. Went to Cambridge. Cambridge was bubbling with Nobel laureates in 1900s because the first Nobel Prize went to J.J. Thomson for discovery of conduction of electricity with the gas molecules. 1908, Rutherford. Lawrence and William Bragg, 1915. James Soddy, 1921. Einstein, 22. He was just interaction with Einstein there. Niels Bohr, 23. And we have a host of Nobel laureates. Homi Bhabha worked with them all. What happens during the World War? He has to come back to India. It's fortunate for our country that Bhabha stayed back, worked with the earlier prime ministers, established the atomic energy program, and his concept of three-stage and all were unbelievable. A person can, come out with so much ideas way back in 1940s. Though basically a mechanical engineer, he turned a full-time physicist later. Thank you all for your kind attention, and any queries I will take now or during the course of the panel discussion. So before I close, I just wanted to one thing. There are two things which I always, when I meet, because a lot of students are there, there are two things I would like to say. One is, whatever you do, even if you go abroad, please come back and serve our country. Number one. This is my request, that consider that Homi Bhabha, P.C. Ray, worked in England, potential Nobel laureate, came back to India, unmarried, bachelor, worked in the laboratory right through his life, established the Bengal Chemicals. J.C. Bose worked in England, and other Bose. They are all work in Cavendish. They all come back to India and served our country. So please do that. The second one is what science and technology can do to society. I'll give you one example. Prior to 1850s, would you believe aluminum was the costliest metal in the world? Would you believe that? It was. Napoleon Bonaparte used to serve food in aluminum plates for only special guests. Came 1882. Two guys like you all, 21-year-old, James Charles Martin and Paul Harat, one from the United States, one from France. They come out with a method to produce aluminum. And it's, what they do is they take the bauxite, they mix with sodium fluoride. Earlier it was a very high temperature process. So they come out with a very simple process. The aluminum cost plummeted. The rest is history. Even beggars don't use aluminum these days. So that's what science and technology can do to society. Two things, the ingenuity. Second is, young guys have done that. So we have a lot of young people over here. I'm sure you all can do that. Jai Hind. Thank you.